Hi everyone, and welcome to the next topic, neural processing in vision. Here are the learning outcomes. We're going to take a look at visual acuity, and that means your ability to see detail. There are a number of factors that affect this, and we'll go through all of those. Another way of thinking about our ability to see is our ability to pick up amounts of light, and that's brightness perception. I'll take a look at that one as well. I also want to put both of these together, as we'll see, trying to measure visual acuity and brightness together into one kind of holistic exploration of the limits of our vision. Along the way, we'll have to take a look at how neural information is processed in the retina. That is something that definitely happens. The retina does not merely pass information back to the brain where processing starts. There's a lot of processing that starts in the retina itself. An important concept is called the receptive field. This is a bit of a tricky concept because you do have to juggle a number of things all together to understand this one single concept, but it is really important. I'm going to be coming back to this concept over and over again, so it's important that you understand it. Tying into this is something called lateral inhibition, so a little bit of anatomical wiring, and this might help us to understand the receptive field, and also it helps explain some lightness illusions. And I am going to be devoting quite a bit of time in this lecture to something called spatial frequencies and the spatial frequency approach, and I'll go through some evidence that our visual system actually does process spatial frequencies. But first, a look at visual acuity, which again is our ability to pick up fine details. We can measure visual acuity. You might have had your visual acuity measured if you've ever been to an optometrist, for example. They use something called a Snellen chart, which is not exactly cutting edge. It dates back to 1862. The Snellen chart does measure your acuity, but it measures your foveal acuity, that is your central vision, as opposed to your peripheral vision. There's nothing inherently wrong with that. We do rely very heavily on our foveal acuity, and it makes sense that you get your vision corrected to normal when it comes to your foveal acuity. Never seen a Snellen chart? It looks something like this. Now I'm hoping you can read the top line and maybe even the second line and probably the third line and maybe even down to 8 and 9. But that's probably because you're sitting right in front of your computer. Try taking as many steps back as you can wherever you are and see what you can see. So that is an important factor. So the size of the letters is pretty important, but your distance from them as well. Like I can read the bottom line. Let me just get real close here. Precision Vision USA, and then there's a phone number, and there's a fax number, and then there's their website. Wait, that's not even line 11. That's below line 11. Okay, it's not fair if I go that close. So this is all about identifying letters. Maybe this one is difficult for you because it's black on white. Here, you can try this one, white on black. All right, so that is the Snellen chart. Now, the thing about the Snellen chart is its units, which is kind of weird. It doesn't really have units. Now, if you take the Snellen test and if it's the proper size and you're the proper distance, for example, when you are sitting in the chair in your optometrist's office, normal is 20/20 vision. And that means you are comparable to other people in this way. So the first number, 20, means what you can see at 20 feet versus how far away does a so-called normal person have to be to see that same line. Okay, so the first number is basically always going to be at 20. Now you might be thinking, but I don't sit 20 feet away from the chart in my optometrist's office. Well, then they've scaled the size of the chart to compensate. So very commonly this criterion 20/200 or worse is considered legally blind. Not that the people can't see, but things are very fuzzy for them. They're going to need very, very thick glasses, and they are not allowed to apply for a driver's license, for example. The problem with the Snellen chart is the unit of measurement. What is the unit of measurement? There really isn't anything that's kind of nice and easy to summarize it as. So then, based on this information from the Snellen chart and your performance, how does the optometrist come up with a unit of measurement because they're probably going to need one if you are not 20/20. So they use what's called a diopter, and that is the reciprocal of the focal length in meters of the corrective lens that will bring your vision to 20/20. Now, there are also units on this. If it's negative, that means a concave lens for people who are nearsighted. If the number is positive, that's a convex lens that's required. That's for people who are farsighted. If you are nearsighted, just to be clear, if you are nearsighted, that means you can see things that are close. You have difficulty seeing things far away, and the opposite for farsightedness. Okay, that's just the clinical aspects, but when it comes to doing research, we're not going to use diopters. In fact, for most research, there's a little note saying all observers had normal or corrected to normal vision. So that's kind of the baseline starting point. So then how can we really talk about visual acuity and ability to see details? Now think back to the Snellen chart. There were two important factors, the size of the letter and how far away you were. We can actually take both of those into account in a measure called the visual angle. It is an angle. It does measure size in degrees. Here's a quick example. Okay, on the left, we have an eyeball, and on the right side, we have a quarter held out at about arm's length. So a quarter is about 2.4 centimeters in diameter, and arm's length is approximately 70 centimeters. Okay, so we have the distance, and we have the size of the stimulus. Next, we have to calculate this angle back here that's cast on the retina. Why angles? Well, you can see that the retina is a bit curved. It kind of makes sense to talk about it in angles, and the particular formula does take into account size and distance. So thinking all the way back to maybe high school or geometry for you, the tangent of angle alpha is the size of the object divided by distance, so 2.4 divided by 70, and if you do the inverse tangent function on your calculator, you'll get this angle equal to about 2 degrees. So a quarter held up at arm's length creates a visual angle on your retina of about 2 degrees. Now, by convention, kind of back in the olden days, they couldn't do decimals. Now, decimals are super easy for us to use now, but back in the olden days, again, they didn't. So there is this history in vision science. So I need to talk a little bit about degrees. Now, yes, you can divide 1 degree using decimal points, but again, by convention, 1 degree is made up of 60 minutes of arc. Now, I know minutes is a unit of time, but here, a minute is a different unit. 1 minute of arc is an angle that is 1/60th of a degree. Now, a 1 degree angle is a pretty narrow angle, so 1/60th of that is going to be a very narrow sliver of an angle, a very, very small angle. Now, minutes can also be subdivided into even smaller units, which are, yes, seconds. So here, 1 minute of arc can be divided into 60 seconds of arc. 1 second of arc is an angle that is 1/60th of a minute. Or, put another way, it's 1/360th of a degree. So it is a very, very, very small degree. This is a bit confusing. You might want to go back and listen to that explanation all over again. Now, the reason I'm bringing up these minutes and seconds and not going with decimals, again, by convention, vision science uses this. And it also turns out that there are some pretty neat ways that these things work out. If you have 20/20 vision, either normal or corrected to normal vision, you should be able to make out details of 1 minute, and this is the equivalent of seeing a quarter at the distance of a football field. So imagine you're on one end of the football field, and there's, let's say, a football player at the exact other end, and they're either pinching their fingers together or they're holding up a quarter in their fingers. you should be able to see the difference if the fingers are pinched together or if they're holding up a quarter. And we can explore this idea of visual acuity, and this raises some important applied questions, which are super important to me. If I buy a high-definition TV, how far away should I sit from it? That's not something you think of? Okay, it's something that you can think of. So the main issue used to be a bit of a trade-off. If you sit too close to a big screen TV, you'll be able to see each pixel, and that's not really good. I mean, it kind of takes you out of the viewing experience. It kind of gets in the way of actually seeing the image and experiencing the movie. But if you sit way too far back, all of those pixels are going to blend together, and it will exceed the resolution of human vision. So you've paid a lot of money for this resolution, and yet you're not able to see the different pixels. So it's kind of a trade-off. And this is what it used to be for the longest time. However, these days you can buy 4K or even 8K TVs, and you know what? It doesn't really matter where you sit, because that resolution is going to exceed your visual system. All of those pixels are going to blend together, unless basically you're pressing your nose up against the TV. And that's really not the best viewing experience. So instead of this kind of issue, it has been kind of shifted a little bit to what's called the field of view, as televisions have gotten bigger and bigger and bigger. So a 50-inch or a 60-inch television is really not that unusual anymore. But again, size isn't everything. It's not just the size, but how close you sit. Now, for a lot of people, they want to be immersed in a movie when they're watching it, but if you're far too close, to look from one side of the screen to the other, you actually literally have to move your head, and that's probably you're a bit too close, so your TV is a bit too big. So here's an example of field of view. So this is a 20-degree field of view that's kind of simulated. So this is the TV screen that you're looking at. Yeah, you can see what's going on the screen, but you can also see a lot of things behind it. And for some people, that kind of does take them out of it. Here is a simulated 30-degree field of view. So this is filling up more and more of your visual field, and there's less and less of the background. And that can be a bit more immersive. So what's the magic number? Okay, so there's an organization called SMPTE, and that is the Society of Motion Picture and Television Engineers, and their recommendation is that the screen should fill up 30 to 40 degrees of your field of view. Not less than that. The screen is kind of a bit too far away. It's a bit distant, both literally and figuratively. If it's bigger than 40 degrees, you're kind of a little bit too close. So how do you know? Time for some math. Okay, here's the formula. You take the size of this screen, and when you buy your TV screen, it'll give you the size of it, usually in inches. You multiply that by this value, and this will give you the distance for a 30-degree field of view. So, for example, typical screen size is 55 inches. Multiply that. That's about 7.5 feet. This will give you a 30-degree field of view. Wait, I have to do math just to watch TV? What's wrong with math? Math is our friend. So this is focusing very, very much on what I would call bottom-up processing, the limits of our vision, for example. But there's also a top-down influence, and that was shown in this study from 2009. So participants, observers were brought in, and they were told they were going to watch some HD TV clips, so high-definition TV. But the other group were told they were watching a digital DVD clip. Okay, so there's a bit of a difference here. HD TV is high definition, a greater resolution. Digital DVD is pretty good, but it's not going to be as good as HD or high definition. They did ask people about their experience, and unsurprisingly, the HD TV group reported that the images were sharper and they could make out more details. Here's the trick. Both groups watched the same video clip, and it was actually a pretty low-quality DVD clip. So what's going on? what people were told influenced their experience. If they were told they're watching high definition, they experienced it as being sharper and more detailed. So just a bit of an aside, this shows a particular cognitive bias called the framing effect, in which top-down processing can influence something as basic as visual perception. So if you've got a TV and you're on a budget, it's not the greatest TV, just tell people it's an 8K, and they might actually believe you. Yeah, my TV, it's a 16K. Yeah, it's a new thing. Now, there are a number of factors that affect visual acuity. I'm going to start off with kind of a special case called hyperacuity. In the case of hyperacuity, people can see details that we really don't expect them to be able to see. So people can make out details of 10 seconds or less. Now, this is not just in general, but in particular, something called a vernier grating. And my example here is of a vernier grating. And these ones are actually touching each other, but they don't necessarily have to be. It's basically some black and white bars, and they are either just a straight line, or in this case, offset a little bit. Now, in the case of hyperacuity, as applied to this class of stimuli, people can see better than the theoretical predictions based on what we know about the resolution of the receptors, their rods and cones. Whoa. But let me just get to that, the expected resolution. Okay, so we're going to be focusing on the cones in the fovea. So, as you know, we only have cones in our fovea. Our fovea gives us our highest high-resolution vision. Now we can actually measure the distance of the cones from each other in the fovea. It is 12 seconds, or 1 micron. So they're pretty jammed in there, pretty close together. Now, based on this number, this gives us the expected resolution, and that is 24 seconds. This is the theoretical limit of our visual receptors, our highest high-resolution vision. And now you're wondering, why did it go from 12 to 24? Okay, let me give you a couple of examples to explain. Okay, these are my drawings of cones, and then the next neuron down the chain. This might be, say, a bipolar cell. Okay, so the cones are spaced about as close as they can get, so 12 seconds or 1 micron apart. That's common in the left and the right examples. Now, in the left, I've got 2 arrows. You can think of those as 2 beams of light. And the question that we're going to ask our observer is, can you see 2 beams of light? Now, in the case on the left, the 2 beams are very close together, and they're perfectly striking 2 adjacent cones, and they're turned white. That's kind of my representation of they're firing, they're turned on. These 2 over here are black, they're not firing. Okay, so the cones are firing, and that leads to these 2 neurons firing. So what do we see? Well, we would see 1 beam of light. We have no idea that there are 2 separate beams of light. In this case on the left, these 2 beams of light are too close together. Okay, let's take the same patch of retina, move it over here, here we go, and now we've got, again, 2 beams of light, but they're a little bit more spaced apart. So we have this left beam hitting this cone, causes this neuron to be active, and then we've got a bit of space. So this cone is not activated, and then this cone is. Now we can experience, potentially, 2 separate beams of light. We've got an active neuron, an inactive one, and an active one. Okay, now we can potentially say and experience that there are 2 separate beams of light. And what we need to get is 2 beams of light that are at least 24 seconds apart. This is the theoretical limits of vision. So then, how does hyperacuity work? As I mentioned, we can make out details of 10 seconds or maybe even less in some cases. Yeah, this is not completely well understood. It's not that it's doing something on the retina, but we have to think, well, what happens beyond these neurons? There is further processing. it might be that there's sufficient processing that happens beyond the retina that can actually separate out this particular case of the hyperacuity. Now, I've just showed you examples here in one dimension. To understand hyperacuity, we'd need 2 dimensions, and it starts to get really complex. The most important takeaway is that further processing can actually enhance our vision. It's not all about the receptors. Okay, so the first factor is this hyperacuity, but okay, we're gonna leave that aside and go back to things that we understand a whole lot better than that. The position in the retina, that is, where are you shining your beams of light? In the periphery or the fovea? Now, of course, the fovea has the greatest acuity. It's our highest resolution vision. And that is because of 3 separate reasons, not just one reason. So one reason, which I've already mentioned, is the fact that the cones are very, very densely packed, about as closely packed as they can get. Okay, that is one important factor, yes. But there are other factors. So we're going to go, again, beyond the level of the photoreceptors and go deeper into the visual system to understand what else is contributing. So the second factor is called spatial summation. Okay, so let me just explain what we've got. On the left, once again, these are some cones, and these are cones in the fovea. Over here on the right, well, these are rods. I've tried to draw these rods, and I've tried to draw them a bit more spaced out than the cones are, because the rods just are spaced out more. The rods are in the periphery, okay? I've got, otherwise, identical stimuli. Over here on the left, 2 beams of light separated by a certain distance, exactly the same thing over here, okay? So the same stimuli is being shone on the fovea or in the periphery. So once again, this is similar to what I showed you in the previous slide. We've got 2 beams of light hitting 2 cones with another cone in the middle, and we can tell that there are 2 beams of light. We've got 2 active neurons with an inactive one between them. So yes, we can differentiate, and we know that there's kind of a dark gap in between those 2 beams of light. But if we do the same thing over here in the periphery, okay, striking a rod there, and we're very lucky it's just catching this rod. So far it's kind of the same situation as the cones on the left. But look at where those rods are sending their signal. Both of these rods are being sent to this one intermediate neuron. This is called summation. So all of these 4 rods are sending their signal to this one active neuron. So the result of showing 2 stimuli shining into the periphery is that we just have 1 neuron firing. We can't tell that there are 2 beams of light because of the convergence of the axons of those rods. So again, it's not just what's happening with the photoreceptors, but what's happening at the next level of processing even. And then we can continue to follow it back, even getting to the visual cortex, so pretty deep into the visual system. So the third component that contributes to retinal position is something called the cortical magnification factor. Now, this isn't magnification of a lens, it's the magnification of the cortex, that is the brain, the outer layer of the brain. What the cortical magnification factor gives us is basically how much brain tissue is devoted in the visual cortex to the incoming information. Now, not all incoming information is treated equally. It depends on retinal eccentricity. Yeah, this is a mathematical term, and it describes our position on a curved surface. What curved surface is that? Well, that's the retina. An eccentricity of 0 means we're right in the fovea, and as those numbers increase, that means we're moving out into the periphery. This has been understood to the extent that we can actually capture the cortical magnification factor in a formula. So if you're mathematically inclined, you can kind of work this out and understand this a bit. If you're not mathematically inclined, don't worry about it. E is eccentricity, so where we're kind of considering on the retina. M sub 0 is a constant called the foveal cortical magnification factor. Now, if you do work out all the numbers and everything, what it tells us is this. The fovea, at an eccentricity of 0, has a proportionally huge amount of brain tissue in the visual cortex devoted to it. Remember, the size of the fovea is very, very, very small, but it has, again, disproportionately huge amount of brain tissue and brain cells devoted to processing that incoming information. This means we can do a lot of processing and extract a lot of information. Now, conversely, the farther away you go from the fovea, there are proportionately fewer cells devoted to processing that information. So this partially explains why, if there's something that falls in your periphery, you can't really see it as well. You can't extract as much information, and your visual acuity is not as good. Now, the fun thing about this cortical magnification factor is what we can do is structure and arrange some letters according to that formula. Now, the way this works is you would look at the dot in the center here and just don't move your eyes away from that dot, okay? Now, the funny thing about these letters is generally the farther something is from your central vision, the harder it is to identify it. But these letters have all been scaled by the cortical magnification factor. So again, without moving your eyes, you can shift your attention to the ring of letters that surrounds the dot. So you can see that they are E-S-A-C-U-I-T-Y. And again, without moving your eyes, you can go to the next ring, A-T-I-O, and the next one, M-A-G, and even the farthest ring of letters. Now you can see them and identify them, of course, because they're bigger, and they're just big enough so that you can actually identify them. So this is the cortical magnification factor, and all of these letters that you can see have equal cortical magnification. There are still some other factors. We have to take into account that the eyes are optical, and sometimes there are focusing errors. Now, I did bring these up before, but let me talk about them in their technical terms. Myopia means nearsightedness. And for people who have this means that the incoming light rays are focused, in the middle of the eye. That shouldn't be happening. They should be focused on the back of the eye back here, but you can see they're not. So as a result, in this case, the person experiences a blurry image. Their eyeball is kind of too long. The opposite is hyperopia, in which the eyeball is kind of too short, and as a result, the focal point is actually behind the eye. So that means when the light hits the retina, again, it's going to be blurry and out of focus. Again, fortunately, we can get lenses that can adjust so that the image does get focused right on the retina and everything is sharp and clear. But other things can go wrong. Oh dear. Like astigmatism. Now, this is a problem with the cornea not being perfectly spherical, but kind of sort of football-shaped. It's called asymmetrically curved. And as a result, not all of the incoming light rays get focused at the same point. So it kind of depends if you're seeing a vertical line versus a horizontal line, as it shows in this example. So the vertical one gets focused here in the middle of the eye. That's going to be blurry. And then the horizontal one, which is the same distance, but it gets focused behind the eye. Oh man, that's going to be blurry too. Again, fortunately, they can construct lenses, corrective lenses, that can sort of help out this problem of astigmatism and make sure everything is in sharp focus. So far, so good. Oh man, but there are still other factors. So again, our eyes are optical devices. They do have a lens in them. Lenses can introduce new problems, like this one called chromatic aberration. So in this case, we have white light coming into a lens, and as a result of the lens, it kind of splits the different wavelengths apart. Now, this is, of course, a tremendous exaggeration, but the different length of wavelengths would get focused in different spots. Again, what you're looking at is a white stimulus, but it's kind of being slowly pulled apart by your lens, which is supposed to be creating things in sharp focus. But again, there may be some chromatic aberration. There's also something called spherical aberration, and now we have to take into consideration where the light rays pass through the lens. Are they passing through the center of the lens or towards the edge of the lens? Yeah, so here's another problem. Again, depending on where they pass through the lens, they will get focused at a, well, slightly different location. Again, this is a massive exaggeration. Now, to minimize this effect, it would actually be better to have a smaller pupil. So the smaller the pupil is, that means it's forcing the light to go through the center of the lens, and it's kind of blocking out the edges. The iris would be kind of covering that up. Of course, there are trade-offs here. The smaller the pupil is, the less light is entering your eye, and under low light conditions, you would not be able to see anything. We still have one more factor affecting visual acuity, and it is another optical property called diffraction. If we have light rays that go through an obstacle or a narrow slit, they will get bent. Yeah. Again, this affects different wavelengths, and it depends on the size of the slit. Without going too much into detail in the physics of this, it would actually be better to have a larger pupil. So in this case, you can imagine this slit is your pupil. So the larger your pupil, the less diffraction there is, and the less of a problem that creates. So the larger the pupil is, the better. Do you remember the advice from the previous slide? It's better to have a smaller pupil. What is the optimal pupil trade-off size? It is 2.4 millimeters. This will minimize diffraction and spherical aberration. And I'll stop this video right here.